We're going to take a look at longitudinal waves. And you have something over here on the left that's creating these pressures. It's pressing in and out, okay? And when it presses in, it pushes these particles against other particles, and those particles push against other particles, and so on and so forth. But these particles, if you look at one of the red dots, they just move back and forth, okay? I don't love this animation for some portions. But think of this, when other things push on that red, they're going to push in that direction. When it pushes on another thing, Newton's third law says there's going to be a backward force on it. So it just moves back and forth in simple harmonic motion. Okay, the parts that we really care about, these clustered in areas, these are called condensations or compressions. They're higher pressure areas. And the area in between is called a rarefaction. Rare, think of things are rare in that area. So the condensations, the areas of high pressure, move in this direction, even though the particles don't move in this direction. They just move back and forth in simple harmonic motion. So the wave velocity is to the right in this one. The particle motion is back and forth, right and left, parallel to the wave velocity, parallel to the transmission of energy. And so longitudinal, a way to think of it is the particles move along, back and forth along the path of the energy transfer. Now, when you're measuring these things, you can see wavelength isn't too bad. Wavelength you could just measure between the condensations or the peaks or the rarest of the rarefactions, so from one part of the wave to the next identical wave. Amplitude is quite a bit tougher. Well, first of all, it's really hard to tell where the center of that condensation is, so wavelength's a little trickier, but amplitude's even harder. If we look at this red dot, the amplitude, it's in simple harmonic motion, so we'd have to know how far it goes to the left, how far it goes to the right, and the average of those two positions would be its equilibrium position. So the amplitude is half of that total motion. So amplitude, very, very hard to measure when we're talking about longitudinal waves. This is just a longitudinal wave on a spring or a slinky. And so you can see the hand is creating the simple harmonic motion that gets transferred down the medium. That's what it would look like. This is a longitudinal wave, and it's just a snapshot of a longitudinal wave. These parts would be moving back and forth, and these condensations or compressions would be moving one way, either to the right or to the left. I'm not sure what this wave is doing. But at this instant, it looks like that. So as I mentioned, to measure is a little tricky. So what I need to do is I need to find one part of the wave, and I'll pick this condensation, which is also called a compression, and the next identical one. And the distance between those two would be the wavelength. I could do from one rarefaction to the next rarefaction. That also would be a wavelength. But it's a little tough to see in the middle there. Where's the center of that condensation, or where's the center of that rarefaction? Amplitude's impossible. The amplitude you cannot tell from this, because I would need to know. I would have to look at a particle maybe right in there, and I'd have to look at that particle and I'd have to say, okay, where does it move? It's moving back and forth between two extremes. And I don't know where it is at this moment. Is it in the middle of its path, at the end of its path? I don't know. So I'd have to find out how far it goes back and forth and divide by 2, because the amplitude of simple harmonic motion is around an equilibrium point, plus and minus a. So very, very, very hard to measure. Now, the fact that these are A, hard to draw, and B, hard to measure, means that sometimes we do something a little different, which is we represent them as pressure graphs, or position versus time graphs, okay? So if it's pressure, you could see this area has a high pressure. So we mark that as high on the pressure versus time graph. Oop, and I'm going to have to undo that. And then in this area, right there, that's a low pressure. So we mark that as low on the pressure versus time graph. So this is one thing you'll see a fair amount of. In audio, you'll see graphs that look like this top. They look like transverse waves, but they're really just graphs of pressure as a function of time. And I'm going to show you that in a moment. This is a much easier way. If this is a graph of position, and I apologize for cutting off position there, if this is a graph of position, then we could actually get the lambda off this. Okay, if it's a graph of pressure as a function of position. Or if it's a graph of pressure as a function of time, then we could find the period, the time for one repetition. So it really, when you see something like a sound wave or a longitudinal wave made to look like a transverse wave, you really have to think about what's being graphed, because this is not how a longitudinal wave looks, right? It is just a graph of pressure or position against time, I should say, against position or time. So always be aware when you see that. Here's an example of me singing a musical note. Now, if we zoom in on this, it'll actually look like what I was just talking about, because this is a graph of intensity versus time. And when we zoom in on me talking, I got to go way over here. You can see it looks almost random. It looks just weird and chaotic, right? But if we go over here to where I was making a musical note, it looks much more like a sine wave, because I have a beautiful, pure crystalline voice. So that is a longitudinal wave represented as a graph of intensity or pressure as a function of time. And really what's happening is at the microphone, my sound waves are pushing in and out on the microphone. And so the microphone is experiencing high pressure and then a low pressure as it kind of bounces back.